Hi, this is Don Kelly. Welcome to my series of 3 videos on Kalman filter implementation for 6 degree of freedom inertial measurement units. A little bit of background. I often use MATLAB or Python as a rapid prototype tool for quickly testing out certain concepts. For the next 3 videos, I'm going to use MATLAB, and I'm going to develop a Kalman filter for a 6DOF IMU. Following these videos, I'll do another series showing how to implement the Kalman filter with an Arduino and an IMU in real time, so you can see how it actually works in real time. So part 1 coming up next. That's to develop this concept, we've got to do 3 things. First of all, we need to develop a simple one-dimensional gyro model in MATLAB. And then what we're going to do is we're going to develop a complementary filter to estimate the angles. And then from there, I'm going to step up to a Kalman filter to estimate the angles. And what's interesting about this is that we'll be able to compare the Kalman filter to the complementary filter and see what the differences are and the similarities and what it takes for each of them to tune, the advantages and disadvantages and such. So let's move on to part 1, which is the simple 1D gyro model. And I'm going to run over to MATLAB here. So I've got a simple test program built, and this has all the pieces in it right now, but I'm just going to cover the gyro piece in part 1. So let's look at the MATLAB code in the center of the screen. First of all, and I've got the font big enough where you can print the screen and type in the variables if you want to run this on your own. It's really only about 10 or 15 lines of code for each of these parts in MATLAB, part 1, part 2, and part 3. So it's not that much. For the gyro, we set up some initial conditions. And this includes defining, and I mentioned it was only going to be one dimension, so I'm going to pick roll, for example, in this. And so I'm going to need to set up a model for what true roll is, and then I'm going to need to set up a model of what the gyro outputs to the complementary and the Kalman filter, and then the same thing for the accelerometer. I'm going to have to develop a model for the accelerometer. The gyro, for example, one of the issues with gyros is they have drift, and so I'm going to simulate that this has a 1 degree per second drift on it. That's what the accelerometer is actually used for, is used to correct the drift. Also, gyros and accelerometers both have noise, so I'm going to introduce some noise into it and make sure that the filters can track through noise. For the time interval, I'm going to use the 250 hertz time step, which is 4 milliseconds. And then I've set up a data storage variable here where I can store variables. So let's skip the complementary filter and the Kalman filter parts for now, and I'm going to go down to the actual simulation. What I'm going to do in the simulation is I'm going to run 2,500 iterations. And remember, this is at 250 hertz, so that means that that's a roughly equivalent 10-second simulation. And to make this realistic, I'm going to move the gyro to 3 different locations. I'm going to add a roll rate in here of 30 degrees per second for a little bit, and then I'm going to do a roll rate of minus 40 degrees per second for a little bit, and then back to 10 degrees per second. So it'll give us a realistic profile, maybe something similar to what a drone might see. So let's get on to the gyro model itself, the IMU model. I'm sorry, gyro and accelerometer. The first thing I have here is a very simple way that I'm going to handle the angle change. And the roll change is going to be the new roll is equal to the old roll plus the velocity of roll times the change in time. So very simple model here. And now I need to come up with gyro and accelerometer measurements that will go into the complementary and the Kalman filter. First of all, accelerometers actually produce micro G's as their measurement. But what we'll see in the Arduino real-time code that I'll show you later is we take that accelerometer in micro G's and we actually do some tricks and we convert it to degrees. So I'm going to skip that step right now and just assume that the accelerometer is going to put out a value in degrees based on the true roll here. So the accelerometer measurement is the roll plus some noise that we're going to insert. Now the gyro is more complicated. The gyro needs to read it needs to read degrees per second. That's what it provides out for us. So we're going to take the true degrees per second, the velocity. We're going to have a drift term embedded in that because the gyro drifts, and some random noise. And then we're also going to have a calibration bias term in there. It turns out that gyros, when you first start them off, they're not perfectly level, and you have to or they have some degree per second bias in them that you need to remove by letting them sit for a while. So we're going to have that in there. The actual measurement then just becomes this reading, and then we're going to take the gyro bias back out of it. So that's the gyro and accelerometer model. It's pretty simple. The only other thing at the end here, we'll take the roll, and I'm going to plot it so we can see what we're actually hoping to get out of the complementary filter and the common filter. So let me run that, and you'll see here's what the actual angle or roll is that this simulation is calculating. So you can see we started at 0 roll, we added a ramp up to about 30 degrees, and then a ramp down to -10 degrees, and then a ramp back up to 0 degrees. So very simple model. So that sums up our gyro and accelerometer model. The next part of this series is going to cover how we do the complementary filter. Thanks for watching.